When alkalinity is added to seawater, atmospheric CO2 is pulled into the ocean and converted into bicarbonate. This stores atmospheric carbon for tens of thousands of years and counteracts ocean acidification by locally increasing pH. Electrochemistry might be key to producing enough alkalinity to securely and affordably sequester billions of tons of CO2 every year. The principle is simple. Seawater is pumped through an electrochemical system where electricity provides the energy to rearrange water and salt molecules into an acidic and basic solution. Removing the acidic solution and returning the basic solution to the ocean will increase seawater alkalinity and pull atmospheric CO2 into the ocean. As for the acidic solution, beneficial uses are being explored, which could also improve the economics of electrochemical seawater treatment. On the one hand, the acid can be neutralized using minerals found in rock that is widely available. Waste finds from existing mineral mining industries alone could absorb the amount of acid that is produced by drawing down 1 billion tons of CO2 per year. Beyond that, additional alkaline or silicate rock could be mined to neutralize the acid and produce useful products. On the other hand, the acid can be used to produce hydrogen gas. If renewable energy is used, this hydrogen would be carbon negative. In a different approach, the acidic solution can be used to extract CO2 from the seawater so that it can be stored elsewhere or reused. To do that, a small amount of the electrochemically produced acidic solution is added to a much larger volume of seawater, which has to be pumped from the ocean into a separate tank. As the acidic solution mixes with seawater, the acid converts the dissolved inorganic carbon into CO2 gas, which can then be removed with the help of what is, essentially, a large vacuum cleaner. By adding back the basic solution and returning this CO2-stripped seawater to the ocean, it can then absorb the same amount of atmospheric CO2 that was removed in the process. The theoretical potential of electrochemical CO2 drawdown is extraordinary, as electricity and seawater are the main inputs of this approach. However, important questions relating to costs, environmental benefits, and scale still need to be resolved. The electricity and infrastructure required to pump and split seawater are cost-intensive, but interesting workarounds are being explored to reduce or offset costs. For example, returning the alkalinity directly to the ocean and removing the acid for later use could almost eliminate the costs of water pumping. Co-locating such electrochemical systems with offshore wind energy would provide both infrastructure and electricity. It's been estimated that the use of offshore wind for electrochemical CO2 removal has the potential to be significantly more efficient than using this electricity to displace CO2 emissions from a coal-fired power plant. Approaches that produce valuable byproducts, such as hydrogen and oxygen gas, as well as silica or nickel and iron hydroxides, could considerably offset the costs of CO2 removal. As long as pH is maintained within the bounds safe for marine life, electrochemical facilities could be co-located with vulnerable coral reefs or sensitive aquaculture farms to locally alleviate ocean acidification. So far, these approaches have only been demonstrated in the lab, and large-scale testing and pilot experimentation in the field are required to validate their effectiveness and test environmental impacts in real-life settings. Scaling of electrochemical CO2 removal will ultimately require a coordinated effort involving science, industry, governments, and local communities to create a permitting system for responsible research and deployment, refine the technology, minimize risks, and develop markets and supply chains. To learn more, please visit oceancdr.net.